Welcome to Chapter 3, where we will explore the physical and chemical properties that make the ocean unique and essential for life. This chapter will cover the chemistry of water, including the molecular structure, hydrogen bonding, and the unusual but vital physical characteristics that allow water to exist in three different states: solid, liquid, and gas, under Earth's conditions. We will also examine the role of density, salinity, and heat capacity in shaping marine environments. Beyond chemistry, we will look at the large scale physical processes like waves, tides, and circulation patterns, and that stratification of the Earth into layers. These properties influence everything from the survival of tiny plankton to global climate systems. Understanding these foundational principles is key to interpreting the biological diversity and ecological interactions we will study later. Keep in mind, the physics and chemistry of the ocean set the stage for all marine life. Matter is composed of elements, each made up of atoms. Atoms can exist alone, like helium, or chemically bonded to form molecules. A water molecule consists of two hydrogen atoms and one oxygen atom. What makes water unique is its polarity. Hydrogen carries slightly positive charge, while oxygen carries a slightly negative charge. This polarity gives water extraordinary properties, making it a life-supporting molecule. The positive and negative ends allow water molecules to form hydrogen bonds with one another, which explains why water sticks together, dissolving so many substances and moderates temperature. These molecules' characteristics are the reason oceans support ecosystems. Life as we know it depends on this chemistry, from cellular processes to global climate regulation. Hydrogen bonding occurs because water molecules are polar. The slightly negative oxygen atom of one molecule is attracted to the slightly positive hydrogen atom of another. This attraction is not strong as a covalent bond, but strong enough to give water cohesion, meaning molecules stick together. Cohesion explains surface tension, allowing some organisms like water striders to walk on water. It also supports capillary action, which helps transport water in plants. In the ocean, hydrogen bonds maintains liquid water across a wide range of temperatures, stabilizing heat, and drives key processes like evaporation and condensation. Without hydrogen bonding, water would behave like a gas at most Earth's temperature, making life impossible. Remember, hydrogen bonding is the reason water is both common and biologically indispensable. Water is unique because it naturally exists in all three states of matter: solid or ice, liquid, and gas, as in water vapor. Hydrogen bonds hold liquid water together across most of Earth's temperatures, giving our planet stable oceans. When cooled, water molecules slow down, forming ice. Interestingly, ice is less dense than liquid water, so it floats, a property that insulates aquatic habitats during freezing conditions. Water vapor, on the other hand, forms when molecules break free of the hydrogen bonds, a process called evaporation. Humidity represents the amount of water vapor in the air. These phases change required significant energy, which helps regulate Earth's climate. For marine biology, the ability of water to exist as liquid, solid, and gas is crucial. It enables climate stability, nutrient cycling, and the persistence of life in aquatic ecosystems. Without this property, oceans and marine life would not exist as we know them. Density describes how tightly packed molecules are in a given volume. As water cools, molecules move closer together, making the liquid denser. For example, seawater at 35 degrees Celsius has more spread out molecules than seawater at 4 degrees Celsius, where molecules are closer and density is higher. Dense, cold water sinks beneath warmer, lighter water, creating vertical mixing that influences oxygen distribution and nutrient availability. Cold water holds more dissolved oxygen than warm water, which is crucial for deep sea organisms. However, once water freezes, the structure traps air spaces, making ice less dense so it floats. This density anomaly ensures that lakes and oceans freeze from the top down, protecting life below. Density is a key factor in ocean circulation, driving phenomena like upwelling and thermohyle circulation. Without density driven movement, nutrients and oxygens could not circulate effectively, limiting marine productivity. Ice is less dense than liquid water because its crystalline structure traps air pockets, making it buoyant. This property allows ice to float, forming a protective layer on the surface of Earth's oceans and lakes. If ice were denser than liquid, it would sink, causing bodies of water to freeze from the bottom up, eventually eliminating liquid habitats. The floating ice acts as insulation, preventing the entire body of water from freezing and preventing ecosystems below. For organisms in polar regions, floating ice provides a habitat and plays a vital role in regulating climate by reflecting solar radiation. In marine habitats, ice influences salinity and density when it forms or melts, contributing to circulation patterns. This simple but vital anomaly in water's density ensures the survival of marine ecosystems in colder environments and highlights why water is so unique compared to most other substances. Water has extremely thermal properties due to the hydrogen bonds. It has a high latent heat of melting, meaning it requires a large amount of energy to melt ice compared to other substances. It also has one of the highest heat capacities found in nature, which is the amount of heat required to raise the temperature. This property stabilizes marine environments, preventing rapid temperature swings that would stress organisms. For example, while deserts can heat up and cool down dramatically in a single day, the ocean maintains relatively stable temperatures. This thermal buffering allows marine organisms to thrive without facing extreme temperature changes. However, shallow water extremely like tide pools are exceptions, since they contain smaller volumes and heat or cool quickly. Water also has the highest latent heat of evaporation, meaning that it absorbs enormous amounts of energy before turning into vapor. This property is central to climate regulation, weather patterns, and water cycle, making life on Earth possible. Water is often called the universal solvent because its polarity allows it to dissolve a wide range of substances. When a substance dissolves, it becomes a solute, mixing evenly within the water. The ocean is extremely a massive solution, containing dissolved salts, gases, and nutrients that sustain marine life. The concentration of solutes in seawater is called salinity, which measured in parts per thousand. The solvent properties of water are crucial for biology because it dissolves ions like sodium, potassium, and calcium, which are essential for cellular functions such as nerve signaling, muscle contraction, and building a shell. For marine ecosystems, water solvent capacity ensures that nutrients and gases circulate, supporting everything from microscopic phytoplankton to large predators. Without this property, the oceans would be chemically inert, unable to sustain complex life forms. Seawater contains many dissolved solutes, but the most abundant are sodium and chloride, which together give the ocean its salty taste. On average, seawater salinity is about 35%, meaning that every 1,000 grams of seawater contains roughly 35 grams of dissolved salts. However, salinity is not uniform worldwide. In regions near rivers, mouths, freshwater input dilutes the ocean, lowering the salinity to about 15 to 25%. In contrast, areas with high evaporation and little freshwater input, like the Red Sea, they can have salinity above 40%. These variations affect water density, circulation, and the distribution of organisms. Many marine organisms are adapted to a narrow salinity range, so changes can stress or kill them. Understanding seawater composition is crucial for marine biology because salinity influences everything from osmoregulation in fish to global circulation patterns. The salinity of seawater averages around 35%, but it varies greatly by location and environmental condition. Near river mouths, the influx of freshwater lowers salinity sometimes to 15 to 25%. In contrast, in closed seas or regions with high evaporation and little freshwater input can see salinity rise far above average. These fluctuations influence water density and circulatory patterns. Marine organisms are often adapted for specific salinity ranges, so changes can cause stress, dehydration, or even death. For example, estuary species are adapted to brackish conditions, while open ocean organisms are often cannot tolerate large swings. Salinity is also a key in thermohaline circulation, where density differences play a drive by both temperature and salinity cause water to sink or rise, redistributing nutrients and gases throughout the ocean. Understanding salinity is essential because it directly links physical oceanography and marine ecology, shaping the habitats and survival of countless organisms. Water's relative transparency is essential for life, especially photosynthetic organisms. Sunlight can penetrate the surface, fueling phytoplankton, algae, and seagrass that form the base of the marine food webs. However, light penetration varies depending on the suspended particles and dissolved substances. Clear tropical waters may allow light to reach over 100 meters, while turbid estuaries or coastal waters may only allow for a few meters of penetration. Transparency controls the photic zone, which is the depth where photosynthesis can occur, which in turn determines the productivity of marine ecosystems. Beyond primary producers, visibility influences predator-prey interactions, camouflage strategies, and even the behavior of the marine animals. For example, many fish depend on light levels to time feeding or reproduction. Thus, transparency is not only a physical property, but also an ecological driver that dictates which organisms can survive and thrive in different marine environments. The balance of water and distilled solutes in the ocean is dynamic, shaped by inputs from multiple sources. Water enters primarily through the rivers, precipitation, and melting polar ice. Solutes, on the other hand, come from the weathering of rocks, input from hydrothermal vents, and runoff from land. These processes constantly add minerals, salts, and nutrients to the sea. Over geological time, the composition of the seawater has remained relatively stable due to the balance between input and removal processes such as sedimentation and pathological uptake. This stability is essential because marine organisms are adapted to specific chemical conditions. For example, shale-building organisms rely on stable calcium carbonate levels, which are influenced by the subtle solute input and ocean chemistry. Seawater contains several dissolved gases, most importantly oxygen, carbon dioxide, and nitrogen. These gases enter the ocean primarily from the atmosphere at the surface, though biological processes also play major roles. Photosynthetic organisms like phytoplankton release oxygen, while respiration by animals and decomposition by microbes consume it. Carbon dioxide dissolves readily and is critical for photosynthesis, but too much can lower pH and contribute to ocean acidification, affecting shell-building organisms. Nitrogen, though abundant, is biologically useful only when converted into forms like nitrite by specialized bacteria. Gas concentrations vary with depth, temperature, and circulation. For example, colder water holds more oxygen than warm water. Marine organisms depend on these dissolved gases for survival, making the balance between input and consumption vital. Conditions in the ocean are far from uniform. Temperature, salinity, oxygen, and pressure all change dramatically with depth and location. Surface waters are warmed by sunlight and well mixed with wind, while deeper water remains cold and stable. Oxygen is often highest near the surface due to photosynthesis, but decreases in the middle depths where respiration consumes it. At great depths, oxygen levels may rise again due to mixing with cold, oxygen-rich polar waters. Pressure also increases with depth, rising by 1 atmosphere every 10 meters. Organisms living in the deep ocean endure crushing pressures unimaginable at the surface, requiring unique adaptations. These environmental gradients shape where organisms can live, influencing distribution, behavior, and evolution. Surface circulation refers to the movement of ocean waters caused largely by wind patterns. Winds, powered by the sun's energy, heating the atmosphere, drives waves, currents, and gyres. These surface currents redistribute heat across the globe, moving warm tropical waters towards the poles and returning cooler water towards the equator. This circulation moderates Earth climate and affects weather patterns such as monsoons and hurricanes. Circulations also determine the distribution of nutrients and plankton, which in turn impacts marine food webs. For example, areas where surface currents bring nutrients upwards are hotspots of productivity. Currents also influence migration routes for marine animals and the dispersal of larvae and spores. The Coriolis effect is the deflection of moving objects, like wind and ocean currents, which is caused by the Earth's rotation. Because the Earth spins continuously, anything traveling over its surface does not move in a straight line relative to the ground. In the northern hemisphere, movement is deflected to the right, while in the southern hemisphere it is deflected to the left. This deflection shapes the large circular current systems called gyres that dominate the major ocean basins. The Coriolis effect is crucial for understanding weather patterns, storm systems, and large-scale ocean circulation. For marine biology, it matters because it determines where warm water and cold currents flow, affecting ecosystems and species distribution. For example, nutrient-rich upwelling driven by deflection supports some of the most productive fisheries in the world. Without the Coriolis effect, currents and winds would flow straight, and the ocean circulation and global climate would look entirely different. Trade winds are steady winds formed when warm air rises near the equator. The cooler air rushes in to replace it. This constant cycle creates predictable east to west winds in the tropics. Trade winds are stronger during the day when the sun heats the land and the oceans, and weaker at night. Beyond the equator, less consistent wind systems occur. The westerlies in the mid-latitudes and the easterlies near the poles. Together, these wind systems drive ocean currents and surface circulation patterns. For example, the trade winds push water westward, helping form equatorial currents and upwelling zones. These winds are vital for distributing heat, nutrients, and plankton across the ocean. Historically, these are critical for navigation, guiding sailing ships across the ocean. In marine ecosystems, the strength and consistency of trade winds influences climate events like El Niño and La Niña, which have global impacts on weather and marine productivity. Despite constant mixing at the surface, the ocean is stratified into three main layers. The surface layer extends to about roughly 200 meters. It is well mixed and warmed by the sun. Most marine life, including phytoplankton, thrive here due to light availability. Below this line lies the intermediate layer from about 200 to about 1500 meters, where a sharp temperature drop called the thermocline occurs. This layer has limited mixing, creating a barrier between the surface water and the deep ocean. The bottom layer, below 1500 meters, is uniformly cold, dense, and dark, with little mixing. Stratification influences oxygen and nutrient distribution. Gases from the surface may not easily reach deeper layers, while nutrient-rich deep waters may remain trapped below. However, upwelling and downwelling occasionally disrupt this regulation, transporting nutrients upwards and gases downwards. In addition to the stratified layers, the ocean experiences vertical movements through processes like upwelling and downwelling. Downwelling occurs when surface water sinks due to the changes in temperature and salinity, carrying oxygen-rich water into deeper layers where many organisms depend on it. Upwelling, on the other hand, pushes deeper, nutrient-rich waters upwards to the surface, often due to wind-driven currents. These nutrients fuel massive blooms of phytoplankton, supporting productive ecosystems and fisheries. For example, coastal upwelling along California sustains one of the world's richest marine ecosystems. Without upwelling, many surface organisms would lack the essential nutrients needed for growth. The three-layered ocean system highlights how physical processes regulate the chemical and biological dynamics of the sea. Vertical circulations maintain the balance of gas and nutrients, making the ocean a dynamic life-supporting system rather than a static body of water. Waves are generated when wind transfers energy to the water's surface. The size of the wave depends on wind speed, duration, and fetch, the distance over open water, and wind blows. The highest part of the wave is the crest, the lowest part is the trough, and the distance between the two crests is the wavelength. A wave period is the time it takes for a successive crest to pass a point. A wave approaches shallow water, their base drags against the seafloor slowing them down. This causes wavelengths to shorten, crests to steepen, and eventually the waves to break, creating surf. Breaking waves move sand and shape shorelines, directly influencing intertidal ecosystems and organisms. Large waves can dislodge kelp, redistribute sediment, and affect coastal ecosystems. While waves are surface phenomena, they play an important ecological role by driving, mixing, dispersing nutrients, and determining the conditions faced by coastal marine life. Tides are the rhythmic rising and falling of the sea level caused by the gravitational pull of the moon and, to a lesser extent, the sun. Water on the side of Earth closest to the moon is pulled towards it, creating a high tide, while water on the far side bulges outward, creating another high tide. Between these bulges, low tide occurs. Most places experience 2 high tides and 2 low tides per day, known as a semi-diurnal tides. Tide patterns vary based on geographical area, local features like islands or reefs or seafloor contours. The differences between high and low tide is called a tidal range, which can be small in some regions and extremely high in others, like the Bay of Fundy. Tides influence mixing of water, nutrient availability, and the daily rhythms of countless marine organisms. For intertidal life, tides define when habitats are submerged or exposed, shaping survival strategies for ecological interaction. Tides vary in intensity depending on the alignment of the sun and the moon. When both are in line during a new moon or full moon, their gravitational forces combine to create spring tides, which produce the greatest tidal ranges, higher highs and lower lows. Despite the name, spring tides occur twice each lunar month, not just in the spring. When the sun and the moon are at right angles, their gravitational effects partially cancel each other, creating a neap tide, which results in a smaller tidal range. These cycles influence not only water movement, but also human activities such as navigation and fishing. For marine ecosystems, spring tides can expose intertidal organisms to longer periods of air or submersion, testing their adaptations to changing environments. Neap tides, meanwhile, bring less dramatic fluctuations. Marine organisms living in the tidal zone must adapt to dramatic environmental changes. During low tides, intertidal zones are exposed to air, subjecting organisms to risks such as desiccation, temperature stress, and predation from land-based animals. During high tides, some of these organisms are submerged again, restoring access to oxygen and nutrients. Many species like crabs, mussels, and certain algae have developed strategies to survive alternating wet and dry conditions. Reproduction in many marine organisms is also timed to the tide cycles. For example, grunion fish lay eggs during spring tides to ensure they hatch under protective high water conditions. Tidal mixing also influences the ability of food, disperse larvae, and redistribute nutrients. For humans, tides determine navigation windows in harbors and access to coastal resources. In short, tides not only shape physical coastlines but also drive the survival, behavior, and life cycles in countless marine organisms.